cell 1 fires action potentials and releases neurotransmitter. What effect does that have on cell 2? EPSP. Okay? So cell 2 has an EPSP. Let's say that is sufficient to reach threshold. Cell 2 will then fire action potentials, and it will release its neurotransmitter, which is GABA. What will that do to cell 3? IPSP. Cell 3 then, is it going to be firing action potentials? No. Is it going to be releasing neurotransmitter onto cell 4? No. Okay? So, when cell 1 is active, is firing action potentials, cell 3 is not going to release neurotransmitter, and we are not going to have an IPSP. So we're moving from IPSP to rest. What effect does that have on the probability that cell 4 will fire an action potential? So we're moving from below rest to rest.
In which cell?
This is, we're recording from cell 4, right? If cell 3 were active, we would have an IPSP on cell 4. But because cell 1 tells cell 2 to inhibit cell 3 does not inhibit cell 4. This lack of inhibition on cell 4 does what? Increases the probability that cell 4 will fire an action potential. Because movement from an IPSP to rest is still a depolarization, right? It's still getting us closer to threshold than we were during the inhibition. Jeanette, did you still have a question?
Kind of. Like, so we're saying if cell 1 fire, that we're saying that if we forget 1 and 2, 3 is normally firing on 4. But because 1 started the chain this time, it's changing it so that increases the probability.
Yes.
Because that's what was confusing me before, because I was inferring that it was just a chain and that 4 was just at resting unless 3 was firing. But since 3 is not firing, it's
so that's why you have to imagine the other synapses there, that there are other neurons that could be exciting cell 3. And unless cell 1 and 2 are doing their thing, we can say, okay, if we didn't have 1 and 2, cell 3 is firing, releasing neurotransmitter.
Oh,
Does that make more sense? Does that answer your question as well?
yes.
Okay. This is actually a very common circuit in our central nervous system, and it's called disinhibition. Yeah.
So you said that for cell 3, we should like imagine that there are other synapses like exciting that, and so then that would be sending an IPSP to cell 4. But what if it's receiving other IPSPs instead of EPSPs? Then how can we assume that cell 4 is already below rest?
Right. So what we were saying is the difference is the presence or absence of cell 1 and 2. In the absence of cell 1 and 2, the cell 3 can fire action potentials, release neurotransmitter, cause an IPSP. When cell 1 tells cell 2 to inhibit cell 3, that is less likely to happen. Cell 4 then is not as likely to have an IPSP, which means that it is more likely to fire an action potential because IPSPs are driving it away from threshold. So this disinhibition, getting rid of the inhibition of cell 3, leaves cell 4 at rest, which is closer to threshold than the hyperpolarization of an IPSP. Liliana?
That was my question.
Okay. So if threshold is up here at -50 and IPSP is maybe down here at -75, -75 is farther away from threshold than -70. So by having cell 2 tell cell 3 not to fire, we decrease the IPSP, which means that cell 4 is going to stay right here at minus 70, which is closer to threshold than minus 75. And as I said, this is a very common circuit. There are some really important cells in our brains that are under tight inhibitory control. And in order for those downstream cells to be active, they have to be released from that inhibition. Okay. Does that make sense?